So I'm going to present some electromechanical manipulation characterization of carbon nanomaterials that we are using scanning probe microscopy in our lab to do this. So I have a brief introduction showing what is scanning probe microscopy, and then some recent studies in my lab on carbon nanotubes, and then on graphene if I have time, and then a brief conclusion. So scanning probe microscopy as a microscopy technique is a magnifier, but I think it's more than a giga magnifier for the nano world. Why? Because, well, SPM, scanning probe microscopy, you have a sharp mechanical probe which interacts locally with the sample surface, normally revealing its properties. That's the magnifier part of it. But I like also to think that we can also change this because we're interacting, so we can not only see but also change the properties. And that's what we're trying to do there. Two examples that we can some kind of collective material manipulation. Here we have an organic bilayer, and by applying pressure with the AFM tip, you can change from this configuration to this configuration. Or another type of material modification, you can use electric field to grow a nanowire type of sensor and use it as a nanosensor. So you can use the SPM to actually construct a gas nanosensor. So you are not doing just imaging, but also modification at the nanoscale. And that's what when we start that, we thought, well, what can we do with the carbon nanostructures, graphene and the nanotubes? And I'd like just to remember that the nanotubes can either be metallic or semiconducting. So the very few things that you can think of are, well, since we have a mechanical probe, we can actually apply some force in the form and see what happens. And the other things that we can do are, well, we can apply an electric field, a strong electric field, because we have a very sharp tip, and then see what happens, or then combine these two. We can apply an electric field, actually inject some charge on the nanotube, then apply force and see what happens. So that's what we started doing. So the first study we did a couple of years ago was this semiconductor metal transition in the form of the nanotubes. Well, there was a work from two professors here from the department which has shown that if you have a semiconducting nanotube like this one, and then we start to deform to this configuration, the band gap vanishes, meaning that the nanotube goes from a semiconducting state to a metallic state when it's deformed. And we try to observe this experimentally. So what we did, we applied, we inject charge and monitor the amount of charge, the charge density in the nanotube as a function of the force we applied. And at the same time, we are monitoring the charge and the nanotube deformation. And the basic result is this. The green dots here, they represent the response for the metallic nanotube. So the amount of charge is basically independent on the force, so it's constant. However, for the semiconducting nanotube, there is a transition. So it increases the amount of charge you can put increase as the force increases, but then it saturates at the same regime of the metallic nanotube. At the same time, in blue here, if you monitor the nanotube deformation, you see the diameter of the nanotube decreases as the force increases, as should be expected. So this sharp transition here of the behavior, not so sharp, but I mean this transition of the behavior of the nanotube is an evidence of this semiconducting matter behavior transition. And this force, the per unit length, and the diameter, they are in good agreement with ab initio calculations which were performed. I don't have time to show. So in this study, we have shown that you can see this deformation-induced semiconductor metal transition in nanotubes using electric force microscopy to monitor the charge density and to deform the nanotubes. This transition is reversible. That when we were doing that study, we asked ourselves, well, how the nanotube deforms, and then we did the experiment of pressing the nanotubes with the AFM tip, and so here's the experimental result. As the force increases, the height of the nanotube decreases as should be expected, but each nanotube deforms in a different way. We start to replot this not as a function of height, but as a function of deformation, d minus h. So again, as the force increases, the deformation increases, but again, each nanotube seems to behave in a different way. So we did some sort of modeling based on our previous work that the force per unit length should be proportional to the local height there. And so I don't have time to explain it. We came up with this equation which says that all the nanotubes, this part of the equation is dependent only on the strain, which should be universal for any nanotube. So if you rescale our graph here with this constant here, then all nanotubes should have the same behavior. And indeed, can collapse all nanotubes on a single behavior. In yellow is our theory with no adjustable parameters. And the theory describes very well the experiment. And a bonus of this theory here is that this parameter that we introduced is actually related to the graphene bending modulus, which is the energy which takes to bend the graphene sheet. And using this, you can actually calculate what's this energy to bend a graphene sheet. And another bonus is that we have shown that the Young modulus for graphene should also have a universal type of behavior. And indeed, that's the experimental data, and our theory described the Young modulus quite well as well. So after that, changing subjects, we decided to do work on determination of the semiconducting metallic nature of nanotubes using EFM. So we're just applying electric field and see what we can get. If by the response of the nanotubes, we can distinguish which nanotubes are metallic and which ones are semiconducting. So basically what we do here is a sample. We will have some nanotubes in there. This is the topographic image, and this is the electrical response of the nanotubes. And here's the same sort of images. And if you look at those images and the line profile, so we have a red line here or a blue line here and here, we always see either a V-type of profile or a W-type of profile. And so we have to call this V-shaped or W-shaped profile. And we start to correlate this with the metallicity of these nanotubes. And we did some Raman scattering experiments, some electric measurements. And what we see is that, well, V-shaped profile always indicate a metallic nanotube, and W-shaped profiles always indicate a semiconducting nanotube. And why is that? Well, we have developed a theory. Well, basically, you have a Thomas Fermi approximation, calculation of the nanotube response, and this is described in this part of the equation. And we also have the response of the substrate the nanotube is on. And you have for the response, for the EFM response, you have an interplay between the nanotube response and the metallic response. And for the metallic nanotube, there is a small effect of substrate. That's why you get a V-shape. For the semiconducting, you have a large effect of substrate. That's why you get a W-shape. So you can come back and actually look at the sample and see that you can directly determine which nanotubes are semiconducting and which are metallic. So, yeah. The decoration of nanotube, I will skip this because we have developed a very simple way to decorate carbon nanotubes with nanoparticles, but I don't have time to explain. Just to show in 1 minute our graphene studies. First, we have done, well, the theory group has done some calculations showing that under pressure, if you have a bilayer graphene in the presence of hydroxyl, this will stabilize in a new configuration which we call diamond ball with an insulator. And we ask, can we observe this experimentally? Well, I think the answer is yes. We have done an experiment where we apply pressure with the AFM tip and monitor the charge. And because we're going from a metal to a semiconducting, there should be a decrease in the amount of charge we're injecting on the bilayer or on the multilayer, whereas for the monolayer it should be the same. And we think that this is some evidence, because this only happens when you have water on it. So we have some evidence for the diamond ball for this transition. And finally, I have recently made this decoration of self-assembled monolayers. So we prepare a solution of these organic molecules and put a droplet on the graphene. The graphene is in purple here, and we always see these monolayers formed by these ripples. And if you do some calculation on these ripples, we see that the molecules, they're always oriented where the ripples are formed by the head groups of the molecules. So we have this in the armchair orientation only. And this induces a substantial doping of graphene. And this doping of graphene is actually measured by Raman scattering experiments. Okay, so in conclusion, there is plenty of room at the bottom. That's Feynman's seminal work or seminal talk. And I'd like to paraphrase him, say there is plenty of room at carbon nanostructures for SPM that we try to explore in our group. I'd like to thank my students and my group, and also the theory and Raman groups, and also the nanomaterials group, which help us a lot. Thank you.